Hello everyone, I am Ananya. Our project is titled as Speech-Based Estimation of Schizophrenia Severity using Feature Fusion. It is an NLP-based early risk assessment system. Project objective. To understand why this matters, consider the schizophrenia affects roughly 24 million people globally. However, traditional diagnoses are often delayed by years because they rely heavily on subjective clinical interviews and lack scalable objective tools. Our objective was to bridge this gap because human speech patterns carry measurable biological markers. System architecture. Three-tier design. Our system relies on a robust three-tier architecture designed for clean separation of concerns. The presentation tier, the application tier, and the data tier. Starting with the presentation tier, users can input data in three flexible ways: uploading an audio or text file, pasting text directly, or recording live microphone audio. This tier handles the interactive dashboard and visualization of results. The data then flows into the application tier for processing. Here, raw text undergoes standard processing before entering our feature extraction pipeline, which extracts both deep embeddings using clinical BERT and a 13-dimensional linguistic vector. These features are fused and passed to our PyTorch ML model for binary classification. Finally, the data tier manages our datasets, stored PyTorch models, and evaluation metrics. Communication between these layers is orchestrated via REST API endpoints. So, this is the live demo of our project, estimation of schizophrenia. How it works: text input, we can paste the transcripts. It is ML powered and it gives clear results and it is a research tool. The user can experience. We designed a highly interactive visual dashboard. Here we are pasting the example text. Users can also seamlessly upload audio or text files, paste transcripts. So after analyzing, we got severe severity of 36%. And you can see the word count, sentence, average sentence length, and readability. And there are linguistic indicators. For front end, we build a fast, responsive user interface. So now we are uploading the another text transcript. So after analyzing it, the severe severity is 45%. And you can see the word count, and etc. It also has linguistic indicators. So like this, you can upload audio files or text files or paste transcripts or use a live microphone to instantly view their risk score. Data routing is handled by Python and Fast API, while we integrated OpenAI's Whisper API for the state-of-the-art live transcription. Finally, the core intelligence, machine learning. Our CNN and multi-head attention fusion model was developed entirely using PyTorch. Tools and technologies. To implement this, we chose a modern high-performance tech stack. For the front end, we used React.js and Tailwind CSS, built with a Vite for a highly responsive UI. The backend is powered by Fast API in Python, ensuring rapid data for handling. For NLP, for NLP and transcription, we integrated OpenAI's Whisper API for highly accurate live speech to text, alongside Clinical Word, NLTK, and SpaceSaver. The core intelligence, our fusion architecture consisting of a CNN and multi-head attention, which is built entirely in PyTorch. Dataset and the ground truth. For our data layer, we used a file named label.csv, which contains our ground truth data mapped to BPRS scores. BPRS is known as Brief Psychiatric Rating Scale. This ensures our machine learning model. Moving on to the data and the infrastructure layer, we wanted to ensure clinical validity and smooth system performance. Our training data integrates BPRS scores. Improvements over base paper. A key highlight of our project is how we significantly improved upon the base paper. The base paper relied on the TVFTC, speech features, which required highly specialized, inaccessible hardware. It was limited to offline batch processing, lacked any user interface, and could only process static audio recordings. Our implementation solves these bottlenecks. We replaced the specialized hardware requirements with pure NLP linguistic features like type token ratio, coherence, and more. Furthermore, we added real time processing via Whisper, developed an interactive web dashboard, enabled multi format inputs. Clinical BERT with a 13-dimensional linguistic vector is also combined in the future feature fusion architecture. Performance analysis. Looking at our training performance over 20 epochs, you can see a highly stable optimization curve. Both the training loss, which is blue line, and the validation loss, which is green dashed line, decreases smoothly and converge tightly together. There is no diverging gap between those two curves, which indicates that our model generalizes well to unseen data and avoids overfitting. The model demonstrates steady convergence and strong training stability, validating our fusion approach. Expect questions here. Be ready to mention that the smooth downward trend shows that your learning rate and attention mechanisms are properly tuned. Challenges and conclusion. Challenge 1. Specialized hardware. The original research paper relied on TVFVTC speech features, which required specialized speech inversion hardware that is not easily available. To overcome this limitation, we used NLP based linguistic features such as vocabulary richness, coherence, readability, and sentence structure. This makes our approach more practical and easier. Challenge 2. Data availability. Obtaining real clinical schizophrenia datasets with PPRS scores is very difficult because patient privacy and limited public availability. Therefore, for this project, we generated synthetic transcripts based on available datasets and research literature to develop and validate our prototype. Challenge 3. Environment setup. Integrating OpenAI Whisper for speech transcription required FFmpeg support on Windows. Configuring the environment and system path correctly was one of the technical challenges we encountered, which we successfully resolved. Challenge 4. Model integration. During implementation, we faced tensor dimension mismatches while combining clinical BERT embeddings with linguistic features in PyTorch. Thank you.